Assalamu alaikum. In this video, we'll be discussing an important theorem in statistics, which is known as Bayes theorem. Bayes theorem is based on the law of total probability. Let's understand this first using an example. So here we see a sample space, which is partitioned into three disjoint sets, B1, B2, and B3. By disjoint, we mean that they do not have anything in common, and their intersection with each other is null set. And then we have another event A on the same sample space. If we superimpose these B1, B2, B3 on A, we get something like this. And from here, we can see that A1 is actually the intersection of B1 with A, because these lines are what are separating B1, B2, and B3. So you can see clearly from this figure that A1, or this part of the event A, is what we get when we intersect B1 with A. So since only this part is there in B1, the intersection is going to contain only this part of the whole event A. So we have A1, which is equal to B1 intersection A. A2, or this part of the event A, is basically an interaction between B2, the second partition, and the event A itself. Please note that we are taking intersection with the whole event A. And since only B2 overlaps with this part, so we get, as a result, we just get this portion of the entire event A. And similarly for A3, we get only this part when we intersect it with B. Now we know that A is actually the union of A1, A2, and A3. And we also know that A1, A2, and A3 are also disjoint. There is nothing common in them. So we can simply add them together. We can add their probabilities. Now, A can be expressed as this. A is equal to, since we know that A is equal to A1, union A2, union A3. So A1 can be replaced by the value we have computed here. A is equal to B1 intersection A, union B2 intersection A, which we get from here, and union B3 intersection A. Now, the probabilities, since these are disjoint sets, the probabilities are simply added. So we have P of A is equal to P of B1 intersection A plus P of B2 intersection A plus B3 intersection A, P of this. Had these been other events, non-disjoint events, then we would have to use the law of addition here, which included a negative some element which was to be subtracted from the additive elements also. But since these partitions are disjoint, we can simply add their probabilities together. And now, using the conditional expression, probability expression, we can compute the value of B1 intersection A. We know that B1 intersection A, or for that matter, any intersection between any two events is the product between the conditional probability and the probability of the given event. So here, we take B1 as the given event, and we calculate the probability of B1 intersection A as P of A given B1 into P of B1. Similarly, for this B2 intersection A, we use the same expression, and we compute it as conditional probability P of A given B2 into P of B2, and similarly for this third partition, which is A3. Now, if we sum all of them together, we actually get back the probability of A. It is basically the law of total probability, which says that if you have your sample space partitioned into disjoint sets, and then you superimpose those partitions over an event on the same sample space, then you can get the probability of that event using this expression, which is P of A given BI, which are the partitions of the sample space, into the probability of these BI, or the partitions. Consider an example. There are 3 bags containing red, blue, and green marbles. Bag 1 has 5 red, 2 blue, and 3 green marbles. Bag 2 has a different composition. It has 4 red, 4 blue, and 4 green, while bag 3 has 4 red, 4 blue, and 1 green marble. A bag is chosen at random, and a marble is drawn from it at random. Now we need to find out the probability for a green marble. Now we know that it is actually being done in 2 stages. First, we choose a bag randomly, and then from that, we choose a marble randomly. And since the composition of each bag is different, the number of green balls in each of them is different. So we can use the law of total probability to find the probability of this event of observing a green ball. Let's take B1 as the event of bag 1 being selected, B2 the event of bag 2 being selected, and B3 the bag B3 being selected, and define G as green marble being picked from the selected bag. Now, the total probability of green ball has three components. It could be that the bag B1 was selected, and then the probability of green ball will be decided based on the composition of bag 1. Similarly, if bag 2 was selected, we'll decide the probability based on B2 and similarly for B3. So we compute this probability of this event of observing a green ball, and we take intersection with each of these partitions, which are actually overlapping with the event of observing a green ball. So first we compute the intersection between observing a green ball and that ball B1 was, the bag B1 was selected. And we do the same for B2, and another time we do it for B3. P of G intersection B1 gives us, by using the conditional probability expression, it gives us B of G given B1 into B1. So this probability is basically calculated based on the fact that B1 is selected. We do not know exactly which bag will be selected, but since we are calculating probability, and for this probability, the event is stated as a fact that B1 is selected. In that case, the conditional probability of getting a green ball is this, which is we have if B1 is selected, if this event has occurred, then there are 3 green balls. And the total number of balls in this bag are 5. So we get P of G given B1 as 3 by 8, and we multiply it by the probability of B1 being selected, which is 1 by 3, because it is equally likely to select any of those bags. So we have 1 by 3, and the probability is calculated as 1 over 10 or 0.1. Then we compute the probability intersection between G1 and B1 and B2, and we get this value 0.11, and similarly for B3, and we get the value 0.03. Now, in order to compute the probability of the green ball, we just need to add up all of these probabilities, which is 0.1 into plus 0.11 plus 0.3, and we get this value, which is 0.24. So there is 24% chance that a green ball will be selected. Now, based on this, we can now understand the Bayes theorem. The probability of A with the evidence that B has occurred is known as posterior probability. First, have a look at this expression here. This is the conditional probability, P of A given B. And here you see a very different expression written, which is not the same as we had been seeing earlier. Here it is P of B given A, and you can see that the events have been inverted here. We were trying to find out the conditional probability of A, and here the expression contains the conditional probability of B rather. So P of B given A multiplied by P of A, because A is given in this case, divided by P of B. And for this probability, B was the given event. We call this probability as the posterior probability. Basically, what we're trying to do is that we are trying to find out the probability, the posterior probability of an event A based on its initial probability, its prior probability, when some more evidence, some more information about the event has been provided. This probability here, this expression is known as the likelihood. It is the probability of B being true given A is true. So this is the conditional probability of B based on A. And here the probability of B is the event that B is true, irrespective of A, whether it occurred or not. So the probability of B given A has occurred is the likelihood. This is prior is the initial known probability of A, and we use the Bayes theorem to find out the posterior probability if now B has occurred. And you can clearly see that the probabilities have been inverted here. The value of probability of A that we use here, although we are trying to find out the probability of A, but here we are trying to find the conditional probability of A. And the value of probability of A that we use here is the initial or the prior probability that we know before the occurrence of event B. Let's understand this with the help of an example. If you know that mom sometimes get headache and the frequency of this event is 3%. And she can have bad moods. And these days, her bad moods have become quite frequent. And the probability of her having a bad mood is 20%. And 80% of the times, this is what you know from the past data, 80% of the times, her headaches, they result in a bad mood. Now, we need to find the probability that she has a headache if we know that she is in a bad mood today. So you just need to find out what is the probability that she's probably having headache so that you may try to soothe her. So here we define B as the event that mom is in bad mood and H as the event that she has headache. And now we use the Bayes theorem to find out the posterior probability of her having a headache if she is in bad mood today. So probability of headache given she's in bad mood is computed by inverting the probabilities using the Bayes theorem. And we we use the values which we know earlier. We have here P of B, her having a bad mood, given she has headache, multiplied by her probability of having headache, divided by the probability of her being in bad mood. So we know that the probability that she gets a bad mood when she has headache is 80% from here. So this is a 0.8 multiplied by the probability of her having a headache, which is given, which is 0.03. And then the probability that she will have a bad mood irrespective of anything is 0.2. So eventually we get the probability of her having headache if she's in bad mood as 12%. So although very low, but still there might be a chance that her bad mood is a result of her having headache.